Linear regression is the process by which we describe the relationship between two or more variables that exhibit some type of linear relationship. If it's just two variables, like an x variable that's being used to predict a y variable, then it's referred to as simple linear regression, and that's what we're going to spend most of our time with. But there are some more interesting problems where you have potentially several different variables x that are all being used to predict some variable y, and that would be called multiple linear regression, but still linear regression nonetheless. So let's look at an example. Child psychologists believe that the age at which a child speaks their first word might be somehow related to the child's intelligence. If a child speaks early, then that might be a sign of high intelligence, and a child that speaks their first word very late in life, that might be a sign of lower intelligence. So to study this, they got a random sample of 21 children, and for each child they recorded the age at which the child spoke their first word, age in months, and then later on in childhood the children were given a Giselle test for cognitive ability, and the scores on the Giselle test were recorded. And so we're looking to see if there's a relationship between the age at which a child speaks their first word and their Giselle test score. So the first thing to do, usually in a situation like this, when we have some x's and y's, is to graph them on a scatter plot, something like this. And there's a lot of ways to make that graph happen. I have already stored the data in list 1 and list 2. My x values in list 1, the age at which the child spoke their first word, and my y values in list 2, the scores on the Giselle test. And then if I do second y equals enter, this brings up stat plot number 1. Make sure that it's toggled on. Make sure that the very first type of plot is selected. That's scatter plot. And by default, it usually assumes that your x's are going to be in list 1 and your y's are going to be in list 2. At this point, I usually do zoom 9, which is zoom stat. And that zooms in the screen on our data, and there's a scatter plot of our data. Some people don't like it zoomed in too much because you can't really see the x and y axis. So you can always press the window button, and I'm going to change x minimum to 0, and I'm also going to change y minimum to 0 just so I can see the x and y axes. But anyways, that's a scatter plot of our data. There's other ways you can get this scatter plot. I've also put this data on Desmos. So on Desmos, you can click on this plus sign and add a table, which I've done. And by default, it's calling the x values x subscript 1 and the y values y subscript 1 because you can have multiple tables in the project. But anyways, I've entered all the data in this table, and those points are automatically graphed. I've zoomed in on the data a little bit and named the x-axis and y-axis appropriately. So there's the same scatter plot in Desmos. Then you can also do it in Excel. Here's our data already entered in Excel. And if I highlight all that data and then do insert graph or chart, and I'm looking for one that looks like a scatter plot, and bam, just like that, that's a scatter plot of our data. So there's a lot of different ways to get a scatter plot of the data. But the point is, we're trying to see if it looks like there might be some type of linear relationship. In this case, it looks like a negative linear relationship because as the age at which a child speaks their first word, as that age increases, the older a child is, the lower their mental ability, according to the score on the Giselle test. So, if we had access to the population of all children, the linear relationship would be described like this, where a value of y is predicted by some intercept term plus some slope term times x. Now, I'm going to just type up here for a moment. In grade school, we usually learn about the equation of a line looking like this, y equals mx plus b. At some point in a little bit higher math, this becomes ax plus b. And for higher ordered polynomials, usually a is the first coefficient. Like when you learn about the quadratic formula, it's ax squared plus bx plus c. But then statisticians, usually when they're doing a regression equation, they put the constant term first and the slope term second. So a plus bx is the format that we usually see in statistics. So that's a little bit different than in, let's say, Algebra 1, because in Algebra 1, the b would be the y-intercept, but usually in statistics, the b is the slope. And then to take this generalization one step further, oftentimes we'll use a b for both of those values. The intercept will be called b subscript 0, and the slope called b subscript 1. And so this is often the notation that's used for our sample, but those b's become betas when we're talking about the relationship for the entire population. So the point is that we need to use our data set to estimate what the intercept and the slope are. So there's 3 equations that will help us get that done with just some very basic summary statistics. First, there's an equation for R. Now, R is referred to as correlation, and we'll explain a little bit later what correlation is, but there's this somewhat ugly-looking formula for R that requires that we know the mean of the x's and the standard deviation of the x's and the mean of the y's and the standard deviation of the y's. Once you know R, you can use that together with the standard deviations to find a value for b, which is our slope. And then once you have the slope b, you can use that value of b with the average of the x's and the average of the y's to figure out the value of a, which is our intercept. So looking at this data here, I've already figured out the summary statistics. The average age, well, we have 21 data points. The average age at which the children spoke their first word was about 14 months, with a standard deviation of almost 8 months. And the average score on the Giselle test was about 93 or 94, with a standard deviation of about 14. So if I plug that into the first formula for R, now mind you, this is not a trivial calculation because there's 21 products here that have to be calculated, and then divided by n minus 1. That comes out to be negative 0.64. And in a little bit, we'll talk about the meaning of that negative 0.64. But for right now, I just want to use that negative 0.64 in the second equation to find the slope. So the slope is that value of R, negative 0.64, times the standard deviation of the y's over the standard deviation of the x's. And that comes out to be about negative 1.1. So that's the slope of our least squares regression line. For the y-intercept, we're going to use this formula. So using the slope we just found and the average of the y's and the average of the x's, we get a value for a of about 109. So therefore, putting that a and b together, the equation of our least squares regression line is 109.8 minus 1.1x. And we put a hat on the y to indicate that this is a prediction for y. It's not an absolute relationship between x and y, but we're using x to predict a value of y. And sometimes that's written in the context of the problem, so the predicted score on the Giselle test is 109 minus 1.1 times the age at which they spoke their first word. So once you've figured out this equation that does the best job of going through the data, by the way, we might add that over here. If I say 109.874 minus 1.127x negative 1.127x, and then I press graph again, there's the line, the so-called line of best fit or least squares regression line, passing through our data. So once you have that line figured out, often we are asked to make a prediction. So for example, predict the score, predict the Giselle score for a child who speaks their first word at age 16 months. So we take our equation and we just plug 16 in place of x. And that comes out to a predicted Giselle score of about 91.8. So if a child speaks their first word at an age of 16 months, we predict they'll have a Giselle score of 91.8. Now, I specifically chose 16 because we did not have a 16 in our data set. We had a child number 16, but we did not have an age in months of 16. But what you can do with the original data is you can calculate something called a residual. So notice our first child here spoke their first word at age 15 months, and then they had a Giselle score of 95. So for our original data, the difference between the predicted y value and the actual y value is called a residual. So that's often written as y minus y hat, the actual y and the predicted y. So the actual score on the test minus the predicted score on the test. So for child number 1, they spoke their first word at 15 months. If we plug 15 into the equation, we get a predicted Giselle score of 92.9. But this child's actual Giselle score was 95. So the residual for this child is the actual score minus the predicted score. So that's a residual of 2.0, meaning that the child's actual score was about 2 points higher than the predicted score. This can be visualized on the graph. So if we look at this graph that I did in Desmos, I've graphed the line of best fit going through the data, and here's the point in question. The child number 1, whose age at first word was 15 months, the predicted y value is this blue dot on our regression line. The actual score on the Giselle test was this green dot right here. And so the residual is indicated by this little red line segment. And points that are above the regression line have positive residuals. Points that are below the regression line have negative residuals. Okay, so there's, of course, several shortcuts to doing all these calculations. First of all, I had to enter the data on my calculator in the first place in order to do all these summary statistics like mean and standard deviation. So we might as well use the calculator's procedure for figuring out the regression equation. And that's a function called linreg, or linear regression. So you do press the stat button and arrow over to the calculate menu, and item number 8 is what we want, linear regression a plus bx. They also have a linear regression ax plus b, but that's more so for, I would say, algebra teachers than it is for stats teachers. Linear regression a plus bx is what we're going to use. And then by default, it's usually expecting the x's to be in list 1 and the y's to be in list 2. And down here where it says store regression equation, I'm going to press vars, yvars, function, y1, so that when the calculator does the number crunching and figures out my slope and my y-intercept, it's automatically going to store that in equation y1 on the calculator. So I press calculate, and there's our 109.87, which is exactly the same that we got when we did this number crunching up here. And there's our slope of negative 1.127. Same thing we got over here. And there's our R of negative 0.64, which is the same R we got up here. And then there's also this other number called R squared that we're going to talk about in a little bit. And it stored that regression equation automatically in y1. So that's one shortcut to doing this. Before I show you some other ways to do this without the calculator, there's several pieces of interpretation that we should be familiar with here. First of all, the slope B, the interpretation in general is it's kind of similar to what we know about slope from algebra, rise over run. When you go over so far in the x direction, how far do you move in the y direction? So usually the slope is interpreted as the amount that y is predicted to change when x increases by 1 unit. So in the case of this particular problem, the interpretation of the slope of negative 1.1 is that for each additional month in age at which first word is spoken, we expect or we predict a decrease of 1.1 in Giselle score. Then this number R that we've seen a couple times now, that's the correlation coefficient. And the interpretation of correlation is that it's a measure of the strength of the linear relationship between x and y. Let me show you this app that I have a link to. The extreme values for R are -1 and +1. So if we have points that exhibit a perfectly linear relationship that has a negative trend, a negative linear relationship, if it's a perfect relationship, R will be either -1 or very, very close to -1. On the other hand, if we have points that follow an almost perfectly positive relationship, then the R will be +1 or very, very close to +1. So those are the two extremes, -1 and +1. If the points just look like a big random cloud, like there's no relationship between the x's and y's whatsoever, then you're going to get a correlation very close to 0. Okay, so that's some basics on correlation. So in this particular case, we got a correlation R of -0.64. So I would say that that's a moderate negative linear relationship between age at which first word is spoken and Giselle score. And then R squared, which is quite literally the value that we got for R squared. So that's about 0.41. R squared is the proportion of the variability in Y that is due to X. Now, there's a lot of different ways of wording that are a little bit more meaningful, I guess I would say, to statisticians, but that's the gist of it. What proportion of the variability is due to X? So in other words, if I go back up to our original data, our Giselle scores are all over the place. If we just look at these Giselle scores right here, for example, we have Giselle score as low as 57 and as high as 121 and all kinds of values in between. So the Giselle scores are kind of all over the place, but they're not just all over the place in some random way. those Giselle scores are kind of all over the place because the age at which first word was spoken is also all over the place. And there's some kind of relationship between the score and the age. So the scores are not just randomly scattered all over the place. They are somewhat tied to the age at which the first word was spoken. Now, it's not a 100% ironclad relationship, but part of the variability that we see in the y values is due to the variability that we see in the x values. So you could say that it's the proportion of variability in y that's explained by the variability in x. Or a better but more wordy way of saying it is, it's the proportion of variability in y that's explained by the linear relationship between x and y. So in the case of our data, we have an R of 0.41. That means that 41% of the variability that we see in Giselle's score is explained by the linear relationship between age and Giselle's score. So that's an interpretation of all the numbers in this printout here. We haven't done an interpretation of A, and I'm just going to blow right past that because usually A does not have much of a meaningful interpretation. Okay, now we can get all of that information and a little bit more information if we do a procedure on the calculator called a linear regression t-test. So again, I already have the data in list 1 and list 2. I go to stat tests, and almost all the way at the bottom is linear regression t-test. And it's also by default going to expect that the x's are in list 1 and the y's are in list 2. And I usually have this inequality sign set at not equal to. And if we calculate, we're going to see the same numbers we saw before. There's our A of 109, our slope of negative 1.1, R squared of 0.41, and R of negative 0.64. So all that stuff is the same. One really important additional piece of information is this number S. So this number S is the regression standard deviation, or the regression standard error. Technically, it's the standard deviation of the residuals. So if you go back up to where I did the original number crunching, the standard deviation of my x's is about 8. The standard deviation of my y's is about 14. But this standard deviation that we're getting from the linear regression t-test is about 11. And the meaning of that 11 is when we use x to predict y, usually our prediction is off by about 11 points. So when we use the age at which a child spoke their first word to predict their Giselle score, on average our prediction is off by 11 points. Sometimes we get a lot closer than 11, and sometimes we're a lot farther off than 11, but on average our prediction is off by 11. That's the meaning of the linear regression S. Then the other thing going on here is that even though we're not going to learn about this particular t-test, the linear regression t-test is a hypothesis test to see if our slope, negative 1.1, that we got from our sample, is that statistically significantly different from 0. Because if the slope was 0, then the correlation would be 0, and we would have no relationship between x and y. So the hypothesis test is to see if there is a relationship between x and y. And so we don't have to really know how the value of t is calculated, but this linear regression t-test calculates a value of t and a p-value associated with it. And also notice in this type of problem, the degrees of freedom is 19, which is n minus 2. And the reason why it's n minus 2 on this particular hypothesis test is because there's two variables, x and y, that are involved in coming up with that value of t. But Having said all that, the main reason that I personally do linear regression t-test instead of just linear regression is the linear regression t-test gives me a value for S. So now let's talk about what that would look like if we were using technology other than the calculator. So in Desmos, we already talked about how to get a scatter plot in Desmos. So now to perform regression in Desmos, remember that this table, my x's and y's were called x subscript 1 and y subscript 1. So we're basically going to write our regression equation, except instead of y, we're going to say y1. And as soon as you type that 1, Desmos assumes that that's supposed to be a subscript. And instead of x, we're going to say x1. And then here's the big thing that makes the magic happen. Instead of the equal sign, we're going to put the tilde sign, which is shift and the number, the key next to your 1 key. So that tilde sign is what tells it to do linear regression. And you see, there's our A of 109. There's our slope of negative 1.1. There's our R squared of 0.41 and our R of negative 0.64. So all the same numbers we got off the calculator. So those of you without the graphing calculator, if you have access to the internet, you can go to Desmos and get the exact same answers. And then you can also do all of this in Excel. So I was showing you before that I have this data in 2 lists in Excel. So if you press on the Data tab, hopefully way over here off to the side, you have a button that says Data Analysis. If you don't have Data Analysis, then you need to go to File, all the way down to Options, and then select Add-ins, and down here at the bottom, Manage Excel Add-ins, Go. And you need to make sure that there's a check mark by Analysis Toolpack. So as long as there's a check mark by Analysis Toolpack, you'll see this Data Analysis button when you press on the Data tab. So we're going to do data analysis, and there's a whole bunch of different analyses that you can do here, but we're going to be doing regression analysis. My Y values are in B1 through B22. My X values are in A1 through A22. I do have labels, age and score. You don't have to have labels, but I have labels. I'm going to have the output range. I'm going to have this print in D1. And I want to get a list of the residuals. We could also get the residual plot if we wanted to. But I think that's good for right now. Press OK. And I'm going to resize these columns a little bit. Resize that one a little bit. And you notice there's our 109 and our negative 1.1, the coefficient of the intercept and the coefficient of age. So our y-intercept and our slope. There's that t value that we got on the calculator from linear regression t-test. Here's the value of s that we got on the calculator, 11.02. So, and there's our value of r squared, which is 0.41. So all of that information is the same. And here's our list of residuals. And look at that first residual, 2.03. Recall that when we calculated the first residual by hand, we got a residual of 2.03. So that's the exact same residual that Excel is handing us. So if you don't have the TI-84 calculator, there's many ways that you can make this regression happen, and many ways you can get the scatter plot and all that type of thing. Okay, so that's about it for regression.